Swayam Prabha. Digital India. Educated India.
Welcome everyone to the first lecture for the Modeling of Multiphysics System course. I am Dr. Abhishek Sarkar and I am an assistant professor from the Department of Mechanical Engineering at IIT Kanpur. For this first lecture, we will go over some of the mathematical preliminaries and we will continue this over the next couple of lectures. Okay, so just a brief introduction of what is multiphysics. So multiphysics, as the diagram shows over here, is a combination of different physical phenomena together to make a system or an entire system. So a multiphysics simulation or a platform is able to simulate transport phenomena, which will be a combination of heat and mass transfer. We will have solid mechanics. So the solid mechanics will be able to solve for the stresses and strains. Our modules for fluid dynamics should be able to solve for flow and flow properties. We can also solve for electromagnetism, that is, if there is a current flowing or there is a changing in magnetic field and due to which some induced voltage is present, we can solve for electric fields and magnetic fields. So electric and magnetic fields. And if we do have a chemical reaction, for example, we have a rocket that is flying and some fuel is getting combusted, or we have a battery system, in that case there is an applied chemical potential due to which some ion is getting transported. So we can solve for chemical reactions. And electrochemical potentials. Okay, so all of these physics together can be simulated. They can be coupled, so we will have a combination of linear and nonlinear systems. We will have a combination of ODEs, which are again linear and nonlinear. We will have partial differential equations. Some of them will be transient, some of them will be steady state. This course will introduce you towards how to select these equations. Whether the equations are required to be solved or whether they can be eliminated or can be simplified in such a way that will reduce the complexity of our model, reduce our computational efforts, and also can give a result that is close to what the real world situation is. So with that in mind, let's get started. So we will start with scalar quantities. So most of us do know that scalars are physical quantities that are completely described by a magnitude. We have mass is a scalar, for example. So mass of a body itself, for example, this table over here is just described by the density times the volume. So it can be a composite, it can have different locations, but the mass at a particular location for this table is a known value. This can have variable mass across, but each point the mass is known by just one quantity. And something to keep in mind is I have written a term called physical quantity. This term will repeat for each case when I talk about scalars, vectors and tensors. So it needs to be a physical or a realistic quantity having some units to describe as a scalar or quantity or a scalar field. We will talk about fields in next lecture, vector quantities and fields and tensors and likewise. Okay, so we have we have a quantity that is completely described by just one content, right? So we will have a matrix. So if A is a scalar, then it is defined by a matrix of A of 1 cross 1. Now scalars are direction independent. That means that if I have a coordinate system and I rotate or translate the coordinate system, then the same scalar quantity, say f, remains f, and that is a function does not change if we move from coordinate system say k, say this is coordinate system k to a coordinate system k prime. Okay, so let's try out a problem. So we have a coordinate system k, and let's take another coordinate system over here as k prime that is slightly displaced and slightly rotated. let's take 2 points, point A and point B, in such a way that the coordinates for A is xi of A or xi prime of A, B and I. Okay. So, what does I mean? So, for each term xi and for either A or B, which means that it is a combination of x1, x2 and x3 coordinates. So, it is in 3-dimensional system. Okay. If we take a difference of the two vectors, these are vector quantities. So, if we take a difference of these two vectors, then delta x for this case, that is the k coordinate system, is equals to xi of B minus xi of A. This is for the k coordinate, and for the k prime coordinate, for the same 2 points A and B, x prime I is equals to xi prime of B minus xi prime of A. This is for the k prime coordinate. Okay. Again, I over here belongs to 1, 2 and 3. Okay. So, for the 3 directions. We will talk more about this I index notation when we go to summation notations. Now, we can see that we have now 2 coordinates. So, we need to have a transformation between the 2 coordinates. How can we transform say x of I A to x of I prime A? So, we can write x I prime is equals to alpha I k, that is our rotation matrix x of k plus some x naught of I. What is alpha of I? This is our rotation vector rotation matrix. So, rotation matrix, it is a matrix of constants, and this is our displacement. Okay. So, the displacement or the translation will move this k to k prime, that is moving it from here to here, and the rotation is turning it from this particular angle and turned it by a certain angle. Okay. Therefore, we can substitute these back into our example. So, delta x I prime which was equals to x I of B prime minus x I prime of A, which is now equals to alpha of I k delta x of k. Okay. So, this nomenclature and this method again is following Einstein summation notation, where k and k are multiplied and summed over. So, it will be for each I, it will be alpha I1 delta x1 plus alpha I2 delta x2 plus alpha I3 delta x3. Okay. Now, these are vectors. What is a scalar is the displacement or the distance between the 2 points. So, so the distance between the 2 points how can we find in the k prime coordinate delta s prime, that is the distance between the 2 points, is square root summation over I from 1 to 3 delta xi delta xi. If I just write it using the summation notation, that is delta xi into delta xi, where just repeating the index over multiplication adds them up. It is in the k prime coordinate. So, we will add a prime term to it. Okay. Now, go to the next slide. Now, let us do our transformation of matrix. So, we had delta x prime of I was equals to alpha I k delta x of k. With this, our delta s prime will therefore be equals to square root of alpha I k delta x k alpha I l delta x l. Okay. For the delta xi prime and delta xi prime, we have replaced it with the alpha terms. Now, we can bring the alpha terms to one side. So, we have alpha I k alpha I l delta x k delta x l, which is equals to now the product of two rotation matrices. So, alpha is a rotation matrix. There is a rotation matrix which is equals to say cos theta minus sin theta cos theta. So, alpha I k alpha IL is actually alpha transpose alpha, which is equals to, if you do this thing, you will find it is 1 0 0 1. So cos square theta plus sin square theta minus sin theta cos theta plus sin theta cos theta becomes 0. Okay, this is an identity matrix, is typically given by delta KL, okay, also called the Kroneker's delta. So the delta KL into delta XK delta XL. Now the Kroneker's delta, again we will go over details for all of these. They have the property that since if k is equals to L, then it is 1, if k is not equals to L, then it is 0, right. So for example, 1 1 is 1, 1 2 is 0, 2 1 is 0 and 2 2 is 1. So we can write the same thing as delta XK delta XK. This looks very similar to our delta S. Okay, so we can prove from this that transformation of coordinates does not affect a scalar. All right. So with that in mind, now scalars are also called zero ordered or zero ranked tensors because they are just 1 cross 1 matrix. They have some properties. They are commutative, that is a product of two scalars A dot B will also be equals to B dot A. We have a distributive property, that is A into B plus C is AB plus AC. Some examples of scalars are given over here, density, energy, mass, they are all scalars, right. So scalars again will have just a magnitude and no direction. Okay. Vector systems, they are quantities, again physical quantities, which are uniquely specified by 3 real numbers in a coordinate system or a coordinate space. So for example, velocity is a vector. So the velocity vector will be given by 3 terms, that is v1, v2 and v3. Okay. Our coordinate system has 3 directions, so x, y and z. Typically we represent directions, for this course we will use e1, e2, e3. So we can also write this as v1, e1 plus v2, e2 plus v3, e3. So 3 real numbers are defining this velocity vector v. We can have other vectors like force vector is f1, f2 and f3. It will be useful for you if you can start using or memorizing vectors as matrices of n cross 1 dimension rather than in this v1, e1, v2, e2 or v1 I cap, v2 j cap, v3 k cap terms. Right. This will be useful when you put it up in a software, either you use MATLAB or you use Python. They do not understand I, j and k. What they understand are vectors and matrices, and it is easier to do vector algebra very quickly and efficiently in these softwares. Okay. So we will consider this notation. This is a 3 cross 1 matrix. So vectors, they do obey the transformation law. What I mean by that is, for example, an A vector prime will be equals to our alpha, that is a transformation matrix, times A, that is a vector, or we can say that A prime of I will be equals to alpha ik, alpha ik A of k. This will actually change the values of this v1, v2, v3 or a1, a2, a3, and this will follow our transformation matrix. So rotation and translation both will affect our vectors, unlike our scalar. All right. So vectors are also defined or called as first rank tensors or first ordered tensors. They are defined by 1 dimension now. So we started with scalars. Scalars were 1 cross 1, that is they had just 1 magnitude. Now we have 1 row or 1 column of values, that is 3 values. That's why they are the first rank tensors for each direction. Vectors do follow laws, that is commutative law and associative law. So commutative law is A vector plus B vector is equals to B vector plus A vector, right. And if I write the components for it, then it will be equals to say A1, A2, A3 plus B1, B2, B3 is equals to A1 plus B1, A2 plus B2, A3 plus B3. All right, and the reverse is also true. Associative means that A vector plus B plus C vector is equals to A plus B vector plus C vector, and likewise. These might look trivial for now. What I am trying to engage you towards is to write these in these matrix format so that these calculations become easier. You don't add component to component as in I cap is added with I cap, j cap is added with j cap. Rather, you start learning this in terms of matrices. All right. So some examples are displacement, velocity, force, and flux. There are several other vectors that you would come across when we would be solving our single physics or multiphysics problems. Now let's go on towards tensors. Now tensors for many of you might be a slightly newer concept. Most of us have learned about scalars and vectors earlier, either from high school to undergraduate. Although our definitions for those were different, vectors we usually defined as something with a magnitude in a direction. I am right now defining this as something that has three physical quantities in which the magnitude is inherent in all the three directions. So when you take a modulus of that vector, say your v vector that was having v1, v2 and v3, when you took a mod v, that is the magnitude, it would be square root v1 square plus v2 square plus v3 square. Right. Tensors are a physical quantity or a property that is uniquely specified in 9 directions, or it has 9 real numbers. So there is practically no 9 direction, that is one direction overlapped onto another direction. Right. A tensor, for example, a tensor can we can start with an example tensor. Let's take a tensor. Tensors are given by 2 bars on the top. Say is given by aij is del ui by del xj. Say u is our displacement vector and x is our position vector. Then del ui by del xj is a tensor. It has 9 components where I and j can go from 1, 2 and 3. So we can write this as a 3 cross 3 matrix that will be del ui by del x1, del u1 by del x1, del u1 by del x2, del u1 by del x3, then del u2 by del x1, del u2 by del x2, del u2 by del x3, del u3 by del x1, del u3 by del x2, del u3 by del x3. Okay. So this is a 3 cross 3 matrix, so it has 9 components, and this defines a tensor. Tensors you can see is a relation between 2 vectors, and therefore tensors are said to be a map that transforms one physical vector to another physical vector. Right. For example, in this case, this vector is called the displacement gradient. So this is a displacement gradient tensor. Okay. So the displacement gradient tensor A will map the position to the displacement. Okay. So we can say in another term that del u vector will be equals to A tensor into del x vector, or in a notation term del ui is equals to aij del xj. All right. So we are mapping one physical vector to another physical vector. That is the objective of a tensor. We can take another example of a tensor, say a higher order tensor that maps our stress to strain. For example, so we know Hooke's law. The Hooke's law, the most common definition is sigma is equals to E epsilon. That is an approximation or a simplification to the first order. So it's a simplified definition. The actual Hooke's law is sigma is equals to C, and that has 4 bars into epsilon. In this case, sigma is a tensor, epsilon is a tensor, and C is called the stiffness tensor. So this is a 4th order tensor which maps a 2nd order tensor that is the stress tensor to another second order tensor, that is a strain tensor. Make sense? Right. So, to map one tensor to another, we need a third tensor, that is in this case is a stiffness tensor. What does the stress tensor map? The stress tensor itself will map our force to our area. Right. So, let's write it down. So, the force vector is mapped to the area vector using our stress tensor. So, this is our stress tensor, and these are our area vector, the force vector. The strain tensor we have already looked, displacement gradient is a kind of strain, or a combination of displacement gradient gives a strain that relates our displacement to our position. The stress tensor relates the area to the force. So, it is two different vectors, right. So, it is mapping one vector of a different magnitude or of a different quantity to another vector of a different magnitude and a different quantity, right. We can also map one tensor to another tensor using a higher ranked or a higher order tensor, like we have seen for the Hooke's law, in which the stress and the strain tensors are mapped with the stiffness tensor. So, the stiffness tensor is a fourth order tensor. Okay. So, there is a difference between a tensor and a matrix. So, the tensors are different from matrices. A tensor maps one vector to a different vector. A matrix will only transform a given vector. Okay. So, our alpha, that was our rotation matrix, would just rotate our vector. It will be the same vector. So, a force will be force, a velocity will be velocity, but a tensor, for example, the stress tensor will map area to force, strain tensor will map position to displacement. Okay. So, the tensors they obey coordinate transformation law. Say the sigma tensor in the prime will be equals to alpha times our sigma, so alpha transpose. So, we have our alpha vector, so these are rotation matrices, so alpha rotation matrices. So, we can see just like vectors, we are able to rotate or transform a tensor, but the tensor quantity does not change. Tensors will therefore be second or higher order or higher rank tensors that will have 3 cross 3 or 3 cross 3 cross 3 or 3 cross 3 cross 3 cross 3, that is a second ranked, third ranked, fourth ranked and higher ranked tensors. Tensors will have a few properties that we can go over. So, for example, S tensor operating over two vectors V and W will be equals to the same tensor operating over V plus the same tensor operating over W, the sum of the two. Okay, that's one. We can have say a tensor acting on a vector multiplied with the scalar V vector. That scalar can come out as alpha, and it will the product of the tensor with the vector V. Okay, so this is possible. We can create a tensor. So, a tensor can be created by using something called a dyadic product. Product of two vectors. So, what I mean by that is, say S tensor is made up of A vector and dyadic product is given by this B vector. This is a dyadic product. Okay, what it means is it is summation over I, summation over j from 1 to 3, from 1 to 3, ai bj, ai cross j. In index notation, it is just ai bj equals to sij. All right. So this is a dyadic product. If you would like to write it in terms of vectors or matrices, then our S, which is a tensor, will be equals to A vector into B vector transpose. So A vector is A1, A2, A3. B vector transpose will be B1, B2, B3. So this will create a matrix of A1, B1, A1, B2, A1, B3, and so on. All right. So this is how this goes in the case of tensors. Dot products and dyadic products are different. In dot products, if I would have done A dot B, it would have been A transpose into B. Vectors are typically in terms of columns. Transpose of a column is a row. So it is if you multiply A transpose B, that is a row times a column, you will get one value, that is 1 cross 1. And if you do a vector dot with multiplied with a vector transpose, you will get a tensor. Okay. So for example, this one is 3 cross 1, this is 1 cross 3, and the output that you get is 3 cross 3. All right. So we can also do tensor additions. So for tensor addition, we have say for example U tensor is S tensor plus T tensor. We can only add tensors which have the same units. So two tensors having the same units, they can be added together. For example, you could add two different direction of stresses into one stress, or split one stress tensor into two stresses. This is typically done in solid mechanics. You can separate out the shear component into one, and you can separate out the hydrostatic component into another. So deviatoric stresses can be broken, and the hydrostatic components can be taken out. All right. Tensor product. So a vector can be formed from a tensor. This we have already talked about. So this is possible. We can also have a product of two tensors. So for example, A tensor is equals to B tensor dotted with C tensor. We have to keep this in mind that tensor products are not commutative. What I mean by commutative is that B tensor dot C tensor is not equals to C tensor dot B tensor. Okay, this is important to keep in mind because we are transposing one in a dot product, and therefore the two of them will not be equal or will not have the same value. Okay, types of tensors. So I will introduce 4 types of tensors for this course, and later on we can try to see if more types come up during the consecutive lectures. Okay, so first is called an identity tensor. So an identity tensor given by I is a tensor in which I tensor dot with a vector will be equals to the vector dot with an identity tensor is equals to vector. So these are commutative. This is the only tensor which will allow in general a commutative behavior. Okay, so I is just an identity matrix. So 1 0 0 0 1 0 0 0 1. Right. Same thing you can do it with a tensor. Second, that is I dotted with a tensor, say S tensor, will give you S dot I tensor will be equals to the S tensor. So you will get back the same thing as an output. Then we have symmetric tensors. So symmetric tensor, for example, S tensor, we can write S as such that it is S11, S12, S13, S12, S22, S23, S13, S23, S33. So the off diagonal terms are equal. Are symmetric, not equal. Which what it means is that transpose of S will be equals to S. S transpose is equals to S, or in index Sij is equals to Sji, and we can see it very well, right? So 1 2 is equals to 1 2, 1 3 is equals to 1 3, and 2 3 is equals to 2 3. So this is an example of a symmetric tensor. An example of a symmetric tensor are stress tensors are symmetric, strain tensors are symmetric, our thermal conductivity is a tensor which is symmetric, and so on. There are many examples of symmetric tensors that exists. Okay, the next one, that's the third one, is a skew symmetric. So once we have done symmetric, skew symmetric follows. So what is a skew symmetric tensor? Is that S say skew symmetric, transpose is equals to minus SS. Okay, so what will be a skew symmetric tensor looking like? It will have all the diagonal components as 0. We will have S12, S13, S23, and we will have minus terms for the off diagonal components. Okay, so SSIJ will be equals to minus SSJI. These are the skew symmetric tensors. An example for it is our omega, which is infinitesimal rotation. Tensor. Okay, so these are our skew symmetric tensors. And the last one is an orthogonal tensor. So an orthogonal tensor, say given by R, is such that R transpose dot with R will give you an identity tensor. Okay, so this is a special type of tensor in which R dot R will give you an identity, which also means that R inverse is equals to R transpose, and the determinant of R will be equals to 1. So the orthogonal tensors are useful when you are mapping one vector space to another vector space of the same length. So they can map one vector space to another of the same length. All right. Some of the examples are of these tensors are stress tensor, strain tensor, thermal conductivity. So thermal conductivity itself is a tensor. We usually take it as a scalar, that is for an isotropic system, but for an isotropic system the heat flux is a vector, is equals to minus k, that is the thermal conductivity and the gradient of temperature. So this is a thermal conductivity which maps our temperature gradient to the heat flux. Likewise, our electric displacement is equals to the electric permittivity tensor times the electric field. So this is electric displacement. This is our dielectric or permittivity tensor. This is our electric field. All right, so we have a very nice documentation which is available that you can go online. If you find the international tables for crystallography, the one I was looking at was the 2006 version, it might be a recent version available. Go to volume D in the chapter 1.1 onwards, you will get a very detailed explanation and understanding of tensors and vectors, how they are mapped, how they are transformed. It will give a very clear understanding on this subject. All right. Now go over to the summation notation. So I have been using a notation throughout in the former slides in which I have been using I and J. So this notation was developed by Einstein, Albert Einstein, in the year of 1960. So they had a set of 3, 6, 9, 12 equations when they were solving for special relativity and general relativity. Difficult to write down. The Maxwell's equations very cumbersome to write. So he came up with this notation method, which became very popular. According to Einstein, so any vector x vector has three components, say x1, x2, x3, and it can be written as xi, ei, where any repeating index is summed over. So repeating index are added, so xi, ei therefore will be equals to summation over I from 1 to 3 xi, ei, where ei is a unit vector along 1, 2 and 3 direction. So that is x1 e1 plus x2 e2 plus x3 e3. Okay, that is the basis of the summation notation. So we can very simply write down this big equation of vectors into smaller equations and with just two terms. So that is the beauty of the Einstein summation notation. So we can see some applications in vectors and tensors. For example, v vector is equals to x vector minus y vector. So we can write vi is equals to xi minus yi, which will give each component of it. So v1 is x1 minus y1, v2 is x2 minus y2, v3 is x3 minus y3. Right. So we can just write, say v1 is x1 minus y1 and likewise. Okay, if we do a dot product, so the dot product, for example, some a is a scalar which is a dot product between b vector and c vector, then we can write bi ci. Now we have already talked that repeating indices are added, so a will be equals to b1 c1 plus b2 c2 plus b3 c3, which is summation over I from 1 to 3 bi ci. Okay, in terms of matrix, let's write it down. So we will have bi and ci, that is our b transpose times c, which is b1 b2 b3 and c1 c2 c3, and which will give you the same output. All right, so this is a quick way to, of writing these. We have simplified this entire dot product for matrix by just one line of equation. All right, for a tensor, so tensors are written as, for example, A is a tensor is aij. So in this case, I and j both go from 1, 2 and 3. We have written this before. So a11, a12, a13, a21, a22, a23, a31, a32, a33. Right. So if we do vector mapping from vector b to vector a using a tensor, or say vector b to vector c using a tensor a. So c vector is equals to a tensor into b vector. So b is a vector, c is a vector, and a is a tensor. So in that case, we can write this as ci is equals to aij bj. Keep in mind that the repeating indices are added. Repeating indices are added. Okay, so which will give me that c1 equals to a11 b1. Now I is fixed in this, that is 1, a12 b2, a13 b3. All right, and so on. C2 will be a21 b1, a22 b2, a23 b3, and same likewise for c3. So these are vector additions. Then we can have tensor products. So the tensor products, they are typically when you are converting two tensors together. Before we go into tensor products, let me just write one more thing down. We have transpose in summation notation. Can be indicated by reversing the indices. For example, A is equals to aij, A transpose will be equals to aji. All right, this is important to note. If we flip the index or if we rotate the index, in that case it will be a transpose. I'll give you one example before we go into tensors. For example, we did this tensor rotation using a matrix, if you remember from the earlier case, in which A prime was equals to sigma into A sigma transpose. That's correct. Okay, how did we write this? So A prime of ij will be equals to sigma ik akl sigma jl. Okay, we can see that these indices are facing each other. So facing each other. That means sigma is not transposed. In this case, these indices are not facing each other. So the repeating index are not facing. In that case, sigma is transposed. So this is the basis of matrix multiplication using index notation. If you have the repeating index on the same side, say xij, yjk, right? So ij and jk, where j and j are facing each other. In that case, it will be a direct multiplication. If the indexes are flipped in one of them, say xij and ykj. So in that case, ij and kj, so the j is a repeating index but is not facing each other. In that case, the y tensor is flipped, or the y matrix is flipped, that is transposed. With that in mind, we can go on towards the tensor properties. So the tensor properties, C tensor will be equals to A tensor dot B tensor. So or Cij is equals to A ik bkj. So you can see that they are facing, so no transpose. Say we have C, which is A transpose B. So in this case, Cij. So we flip these, Aki bkj. So this is flipped, so not facing, or A is transposed. Similarly, we can have A B transpose, or Cij will be equals to Aik bjk. Again not facing, B is transposed. So, so these are the properties for vectors. Derivatives can also be done. We will talk about derivatives in next lecture, but just to introduce, for example, we take a gradient, say u vector is the gradient of a scalar, that is v. So v is a scalar, which means that this is equals to del v by del x1 e1 plus del v by del x2 e2 plus del v by del x3 e3. So we can write ui is equals to del v by del xi, and this can also be written as v comma I. So comma can also be used for gradients, or typically used for gradients. Comma I means del v by del xi. Time, so this is spatial derivative. Temporal derivatives are given by a dot. That is very conventional. So a du by dt, where u is a vector, can be written as u dot of I ei. Okay, so that is du1 by dt, du2 by dt, du3 by dt are the three components. Some special tensors. So the first is a Kroneker's delta. So the Kroneker's delta tensor is the identity tensor. Okay, it's given by del ij. It is equals to 1 if I is equals to j, and equals to 0 if I not equals to j. So del ij matrix is 1 0 0 0 1 0 0 0 1. The property of del ij is such that del ij is equals to an inverse of del ik into del kj. Okay, so you multiply two tensors and you invert one, so A inverse A is equals to identity, and that is our del ij. The beauty of del ij, or the property of del ij, is that if I have a repeating index, say del ik, del il, then this is equals to del kl. So if I and I are repeating, then we collapse it into one del, and that will be del kl. So this is the property of this. Then we have a permutation tensor. The permutation tensor is also called the Levi-Civita. It's given by epsilon ijk. This is equals to 1 if ijk are in even order, 0 if any of the two or all of them are equal, and -1 if ijkn are in odd order. So what I mean by even order and odd order is that if it is ijk, jki, so the order is ijk, jki, kij, then it is 1. If it is in an opposing direction, say we have jik, then we have ikj, and then we have kji, then it is negative. That is -1. Okay, this tensor is typically used in cross product. So if C vector is equals to A vector cross B vector, then Ci is equals to epsilon ijk, aj, bk. So we can test it out quickly. For example, say A vector, we can just take two components for a quick calculation, a1, a2, 0, and B vector is b1, b2, 0. If C vector is A cross B, that is a determinant, I'm sorry. We have e1, e2, e3, a1, b1, a2, b2, 0, 0. Then this will be equals to, so it will be e1 into 0, e2 into 0, and e3 term will have a1, b2 minus a2, b1. Okay, so our vector will look 0, 0, a1, b2 minus a2, b1. Let's try it out with our index notation is epsilon ijk, aj, bk. Let's try out C3. So C3 will be equals to E3 jk, aj, bk. So our terms can be E3 1, 2, a1, b2 plus E3 2, 1, a2, b1 plus E3 1, 1, a1, b1 plus E3 2, 2, a2, b2. All right. So these can be a possible term. So we can also have A3, 3, 3, A3, B3, and so on. Right. So we can have further terms in this case. Again, these terms are repeating indices are 0. What we will have are just these two terms. So 3, 1, 2 is in order, that is Kij. So that is plus 1 into A1, B2. And E3 2, 1 is in reverse order. Again, let me write it down, I, J and K. If we have this order, so I, J, K, K, J, Ki and Kij, that will be positive 1. And if we are in the reverse order, then we are negative. Okay, so minus 1, A2, B1. So that is A1, B2 minus A2, B1. Now what I will urge you to do is try out the other two components, that is C1 and C2, and see if this matches. All right. All right, so we are towards the conclusion of our first lecture. So we will just briefly go over some vector products. So A vector dot with B cross C is equals to B vector dot C cross A is equals to C vector dot A cross B. So we can write this again in terms of index notation. So A vector dot with B cross C is equals to AI and then product with epsilon of I, j, k, b, j, c, k. All right, and likewise you could do the same with bi, epsilon I, j, k, c, j, a, k, and likewise, right? So try it out, give it a try and see if they are equal. You have to use the property of this. So in this case, I and I are repeating, that means it will be added over I, and then we have j and j repeating, it will be added over j, and k repeating, we will add it over k. This can be written as 3 summations over I over j over k of epsilon I j k a I b j c k. Okay, you will find out that they are equal. Dot product of a cross product. So a vector dot a cross b. We know that this is equals to 0. So a cross b gives a vector perpendicular to the both a and b, and dot product of the vector with the same vector but in perpendicular direction is equals to 0. So let's give it a try. So in this case, this will be ai of epsilon I j k a j b k. Okay, let's give it a vector, say c, or a scalar c. So this is a vector, this is a vector, dot product of two vectors is a scalar. So this is epsilon I j k a I a j b k. We can expand this out. So this will be a1 a2 b3 epsilon 1 2 3 plus a2 a3 b1 epsilon 2 3 1 plus a3 a1 b2 epsilon 3 1 2, and then we will have the other terms a2 a1 b3 epsilon 2 1 3 plus a3 a2 b1 epsilon 3 2 1 plus a1 a3 b2 epsilon 1 3 2. Okay, I have skipped over writing all the repeating terms because those are 0. So these are just the positive and negative terms. So the first set of terms are plus 1. So these are plus 1, and the bottom set of terms are minus 1. So minus 1 minus 1 minus 1. We can see a1 a2 b3 a2 a1 b3 will cancel out. These will cancel out, and these will cancel out, and this comes out to equals to 0. Similarly, self cross product is 0, a cross a is 0. We can quickly test it out. So c vector is, say, a vector cross a vector. We can write this as ci equals to epsilon I j k a j a k. And we can expand this. So say C1 is equals to epsilon 1 2 3 a2 a3 plus epsilon 1 3 2 a3 a2. Again this is plus 1, this is minus 1. So this is a2 a3 minus a3 a2 is equals to 0. C2 is equals to epsilon 2 1 3. Again I am leaving over or I am not writing the repeating indices. Those are anyhow going to be 0, and just is a waste of space to write. So we are just writing the terms which will be plus 1 or minus 1. So C2 is I is 2 2 1 3 a1 a3 plus E 2 3 1 a3 a1. Again this is a1 a3 minus a3 a1 equals to 0. Likewise C3 is 3 1 2 1 a2 plus 3 2 1 a2 a1, which is equals to a1 a2 minus a2 a1, which is equals to 0. In the last one, I'll give you a property. Since it's a triple cross product, we have 3 cross products, means we will have so A cross B cross C. You will have a cross product between these two. Say this will give you an epsilon I j k b j c k, and then you have a cross product between this that has an I index and ai. Say you can write it as and some index L and epsilon k L I. Okay, so something like that. So what we are getting up to, that we have 2 epsilon terms, that is 2 permutation tensors, and we have a property for that. So epsilon I j k epsilon LMN, the product of two permutation tensors is delta IL, delta JM, delta KN plus delta IM, delta JN, delta KL plus delta IN, delta JL, delta KM minus in brackets delta IL, delta JN, delta KM, delta IN, delta JM, delta KL, delta IM, delta JL, delta KL. Okay, so you can try this at home and using this property. So very quickly see I, J, K are consistent. We have LMN, MNL, NLM, LNM, NML and ML and N. So the first is in order, in that cyclic order, the second is in the reverse cyclic order, and this property when applied to this triple product will give you the solution. So try and practice these problems, and we will meet in next lectures, in which we will go on towards vector calculus and field theory. Thank you so much for attending today's lecture.